Thank you all for having me. As you can see, I'm not a physician nor a biologist, but rather an applied mathematician. What I would like to talk about today are some mathematical models and mathematical approaches that hopefully will lead to useful tools for the medical community down the line. I have no conflict of interest. So before I begin my own work, I wanted to talk a little bit about the value of a mathematical model, as many of you may not be quite familiar with what one is. It's another quantitative approach. You might probably be familiar with bioinformatics and biostatistics. And so math can be pretty useful in a variety of settings, I think, relevant to myeloma. One is the basic science. The first thing is it links mechanisms to phenomena in a sort of much more rigorous, concrete manner than what human intuition or verbal arguments alone can do. Second approach, or second value, I should say, is that it can be used to generate hypotheses. Meaning what happens is you spend some time developing a model in collaboration with a mathematician, and the results are not what you expect. And more likely than not, it's because the mathematician didn't do his job correctly, or you didn't explain things correctly. But very often, or sometimes I should say, what happens is that the unexpected result really is there, and you've now generated a hypothesis. Moving along to things that are a bit more practical, a higher fidelity model, one that has many more elements and has gone through a lot more testing than one you would use for basic science, could be used for rapid initial screening of certain drugs and therapies. And then sort of the holy grail, what we want eventually is our predictive models, very, very high fidelity models that can facilitate patient-specific medicine. In our case, we want to take something, let's say, like a bone biopsy and use it to basically run through simulations of what different sorts of drugs might do for that patient in particular. So some mathematicians have used Picasso's bulls as metaphors for mathematical modeling, and I think it's an apt comparison. And mathematics is like painting a sort of a representation. And what you have here are various levels of detail. And right off the bat, you might think, well, the best way to go is with the most detail possible. But one can argue that the most detailed model, in addition to taking a lot more time, a lot more thought, might hide essential features rather than illuminate them. And if we're trying to do basic science, we might prefer the simpler model and build up from there. And that's generally one of the things that's quite important, is that when developing a model, there's an advantage of starting with the simpler system and adding complexity from there. So in addition to different levels of abstraction, the nature of abstraction in mathematical models is also probably something that's not completely intuitive. One of the things we want to do is we want to emphasize the important relationships. Down the line, potentially we can put in everything that you can imagine is in a system into a model. But at first, when we're dealing with the simpler models, we want to emphasize those important relationships. And like a cubist painting, those relationships may not seem intuitive or representational at first, but once you spend some time with them, you realize that that is the more valuable or deeper representation of the system. Another issue is that we want to represent things by what they do rather than what they are, meaning that in a model, things have function rather than description. So the project lineage thus far is we began with a non-spatial model, meaning we're looking at just at the local interactions of the various cell types. And we started with a model of normal bone remodeling taken from a Komarova et al. Paper in 2003 that was published in Bone, the journal Bone. And the key feature of this is that it had power laws for the equations, or for the cell type equations, that implicitly captured the cell signaling, the autocrine signaling and the paracrine signaling, rather than individual compartments for those models. And so in the context of Picasso's bulls, this is not the very simplest representation, but it's about one step up. And if we're going to start with bringing in myeloma into a situation, into the normal bone remodeling situation, we didn't want to spend our time with the very more, starting off with trying to find a more complicated model. Now, there is the option to do so, one that doesn't include absolutely everything, but includes quite a bit more than a Komarova model, is a model that Pivanka and collaborators published more recently. And I also believe this one is in Bone. And what you would think is, well, this is potentially an approach that would form the basis for what we would call a more mechanistic model, that the explicit aspects of the cell signaling would be in the model and would consequently need to be measured. So this is the diagram with which we built the model. And what we have in the white arrows, well, except this one should be perhaps red or a different color, but these white arrows are this is a diagram essentially of that 2003 Komarova model, where the normal autocrine and paracrine interactions are modeled and represented using parameters, numbers, that represent the strengths of those interactions. Then on top of this model, what we did is we added a tumor equation and added the effects of the tumor on the system and the effects of the system on the tumor. And that essentially summarizes the model. Now, from the perspective of a mathematician, a model like this is, or a diagram like this, I should say, is extremely valuable. First of all, it's simple. It's something we can take right off the bat and write down some equations quite quickly. And also in this case, my collaborator, Claire Edwards, had gone through the trouble of deciding what were the important relationships. Every specific chemical possible, every specific signaling molecule is not represented, but rather, the families of factors that are paracrine factors, family of factors that are autocrine factors are what are represented in this model. So to summarize what we did, we took those Komarova power laws and we modified them with a tumor term, essentially. And so the system still has cell signaling, it's just that there's no individual compartments for the cell signaling. Rather, the cell growth and decay equations are modified by these factors. And then because we actually have, in a normal bone remodeling situation, we wouldn't have myeloma cells, so we add an equation for growth in myeloma cells, which can include the effects of a proteasome inhibitor. And the word effects is highlighted for a reason. Again, it's the function rather than description of what's important. And so in our case, well, what's a proteasome inhibitor? So what's a proteasome inhibitor to a mathematician? Something that has direct anti-myeloma effects and direct stimulation of osteoblast differentiation. So if we put those into equations, we see something that I think, if you're not used to mathematics, seems like a bit of a zoo. This is a bit of a mess. But by the standards of what you see in mathematical models, this is an extremely compact representation. It's, like I said, it's one step up from the simplest model we could conceivably think of. And in it, unfortunately, I didn't put a slide up of the original Komarova model. The G11 was just sitting here as a power by itself, and all of this would not be here. The G22 sits by itself. All of this would not be here. And so the original model was much simpler. And then we put in the tumor modification terms here, add a tumor equation, and then we put in where the effects of a proteasome inhibitor would be in this V1 term and this V2 term. Not shown in this set of equations is another equation that basically, it's a bookkeeping equation that would keep track of the bone mass as a function of the osteoclast and osteoblast activity. And again, one of the things I also want to emphasize in this model is that we only have compartments for osteoclasts, osteoblasts, and the tumor, the cell types involved. What we don't have compartments for are the individual signaling molecules. Those come in through these factors R11, R21, R22, and R12. And so as well as the G11, G21, G22, and G12. And this is it's a standard approach in biochemistry where you use if you don't have a very complicated model or don't wish to have a complicated model or don't have the inputs for a more complicated model, don't have the understanding, you can do something like this, which is referred to as being a phenomenological model. And this was published by myself, Claire Edwards, Glenn Webb, and John Wixwell in Biology Direct in 2010. So this is a very simple model, but it was found to reflect accurately the very basics of myeloma bone disease. In particular, we found the tumor burden is decreased and bone volume and markers of bone formation are increased when we, in response to a proteasome inhibitor, we got similar pictures for what happened in the effects of myeloma when there was no treatment, as well as the normal bone remodeling. So what we're working on now, or what we want now, is a spatial model The paper we wrote in 2010 did have some spatial models, but they were fairly low fidelity models that really only worked on very limited scales, spatial scales. And the key is we want to embed the models for the local interactions into a spatial model. And we want to try to capture what's being seen in sections of bone marrow biopsy. So the first thing we do, we have to start with things that are simple, is basically we said, okay, well, let's start with normal bone remodeling, and we'll do a 2D formulation rather than a 3D formulation. And we'll use this mathematical method called a level set formulation that comes from, it comes from physics probably, like almost math, but it's been used very, very heavily, for example, in medical imaging. What it does is it captures the interfaces between regions very, very well and gives you lots of very natural, effective tools for evolving an interface. And in our case, the interface of interest is the bone marrow interface. And then after that, we want to think about the refinement and parameterization of local dynamics. So what does the word parameterization mean? We can think of a mathematical model as a black box. You give it some inputs, and outputs emerge. Well, what are the inputs? Especially if we, down the line, if we want to do things that are patient-specific, we need to have a means of parameterization that's highly accurate, high-fidelity parameterization. And so, although I'm talking about a spatial model, probably 90% of the work is going to, in terms of getting this to where it's useful to this audience, is in the refinement and parameterization of those local terms, and think very carefully how we want to capture all the various molecular species that are floating around in the system. So the first work is really just a proof of concept for our spatial model. So we're going to use a level set to define the regions of bone and marrow. So we're either in bone or in marrow. And the interface moves according to the local dynamics of the interacting cells. And this is and we're dealing with no myeloma case, and those cell types have to be simulated. So we're not just doing the interface. Once we have the regions of bone and marrow, we still have to have these cell populations within the marrow. But what moves or what changes, where bone is and isn't, is the local dynamics, is what the osteoclasts and osteoblasts are doing. And so it's still that basic model is still the driver. It's embedded in this larger spatial model. We're picking a circular geometry for illustrative purposes and simplicity. The level set method is actually designed for very, very complicated geometries. Like I said, it's used in medical imaging and those sorts of applications. One reason to start with a circular geometry is we put in a simplified version of the bone remodeling process. And in our simplified version of the bone remodeling process, the bone density goes back to where it was when we started. And so if we want to make sure we're deforming things correctly, starting with a regular circle, deforming it to something that's not, and then having it grow back to a regular circle was an important test of the method. So here, starting at t equals 0 days in our simulation, we start with idealized circular section of trabecular bone. And at t equals 20 days, which I believe was the height of the osteoclast activity or density, we got a certain level of bone deformation. T equals 30 days, most of the bone has been remodeled. And then it takes out to about t equal 150 days for the tail end of the process to finish and the edges to be roughed out. Now, again, this is proof of concept, and so one of the things we want to show is that, we can compute the densities of the cell types, osteoclasts and osteoblasts, and we've actually done simulations with explicit concentrations of rank L and OPG concentrations. I didn't put it in there, but we have models with some of these concentrations. And once we this is a sort of a machine, and so the details of what we put in right now is not so much important as getting the machinery to work. And then once we have the machinery there, we can put in chemical species as we wish. We can pull out, add, do different things with the different cell types. When we did put in the rank L and OPG concentrations, we didn't get essentially any, different results. But again, we were dealing with a highly idealized model and a fairly simple geometry and system. But ultimately, it is these local osteoblast and osteoclast interactions that drive the bone marrow interface in our simulation. And so I just want to show you one slide where we've actually computed these explicitly. And so here, these are osteoblast concentrations. And so we start at the beginning of remodeling process. We don't have any. We only have osteoclasts. Then at t equal 20 days, the osteoblasts are starting their job. T equal 30 days, they're largely finished and they're beginning to disappear. At t equal 150 days, the modeling process is done and there's neither of the species are present. So the level set method that I showed, or level set method computations that I illustrated, I use an idealized circle, and I wouldn't go to the level set if I only cared about a circle. Really, we want to capture down the line much more complicated geometries. And so these are, I think, from a mouse femur that Claire gave me. And one of the things that's interesting is that there are basically two, so this is myeloma progression as we're going along. That's not actually, as a mathematician right now, what I'm stressing about. What I'm stressing about is there's lots of interesting geometric features within these areas, and I wanted a framework that would capture that. And so the level set method is in fact designed for these, and there's regions of essentially marrow and bone and not bone, bone and marrow. And so this is a 2 millimeter scale, this is a 100 micron scale, and the same mathematical framework, the same machine, the same black box will work for a range of scales, probably starting around 100 micron and going up to whatever. There's what's called a continuum hypothesis. Once we get down to where the cells are very, very discrete individual entities, the level set method and other sorts of continuum approaches break down, and you have to use individual based approaches. But for about this scale up, about the 100 micron scale up, the level set is, I think, the right approach to go mathematically. So that's all I wanted to say today. I want to thank my graduate student Jason Graham, who did the level set computations, Claire, Glenn, and John at Vanderbilt, who were my collaborators on the first effort, and we're still continuing to talk. We met at the Vanderbilt Integrative Cancer Biology Center, which is one of these NSFP 50s, and it's designed specifically to bring in mathematicians and biologists together. The level set formulation of the model was done with, done with and helped framed by Jim Martin and Prem Ramakrishnan at the University of Iowa Orthopedics and Rehabilitation. And finally, I'd like to thank Regis Bataille and the organizers of the 13th International Myeloma Workshop for their kind invitation to a mathematician to speak here. Thank you very much.